This is a tutorial on understanding partial fraction decomposition. Now, the idea behind this concept is to take a rational expression and be able to simplify it into multiple smaller fractions. And we're going to explore this concept by looking at a few examples. So let's take a look at the first one. So here we have the rational expression 20x squared minus 60x plus 100 all over x cubed minus 3x squared minus 4x. Now the first step in doing partial fraction decomposition is to first find all the factors that are in your denominator. So for us, we want to find all the factors for x cubed minus 3x squared minus 4x. Now the first thing we could do with this is pull an x out of each of the terms. So when we do that, we'll be left with x squared minus 3x minus 4. So now we know at least one of the factors, which is x. And at this point, we want to see if the x squared minus 3x minus 4 can be reduced further by factoring, which in this case it can. We could change it into two binomials, which would be x minus 4 times x plus 1. Now we've fully factored our denominator. So let's change our denominator to look like this, which is still the exact same expression as it was before, but now we could see all of its factors as well. Now the reason we do this is because when we create the multiple smaller fractions through partial fraction decomposition, these factors will become the denominators. So for example, we'll have a fraction with a denominator of x from our first factor, and then we'll have another fraction with a denominator of x minus 4 based on this factor, and then we'll also have one more fraction, this time with a denominator of x plus 1 for this factor here. Now that we know what our denominators will be, we need to determine how our numerators will be set up. And the important part to this step is to know what a proper rational expression is. Now, a proper rational expression is where the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator. So for example, if we look at our first fraction, we'll notice that in the denominator, our polynomial, or in this case our monomial, has a degree of 1, since the highest exponent in the expression is 1, which in this case is invisible. Now in order for this fraction, or this entire rational expression, to be proper, the numerator on top must have a degree that's less than that, which means it must be a degree of 0. Now if you have a 0-degree polynomial, you'll actually only have a constant. So in this case, let's signify that constant as a. Now when we do the same thing for our second fraction, we'll notice again that in the denominator we have a first-degree polynomial, which means we need to have a 0-degree polynomial on top, or in other words, a constant. And since this constant may be different than our first one, we'll signify it with the letter b. And then same thing with our last fraction. Again, we have a first-degree polynomial on the bottom, so we must have a constant on the top. And it may be different than the other two, so we'll signify it with the letter c. Now that we have our basic setup, we need to do some algebra to solve for a, b, and c. Now the easiest way to go about this is to first clear out all our denominators. And the quickest way to do that is to multiply this entire equation by the denominator in our original expression, which is the x times x minus 4 times x plus 1. So let's multiply everything by that. Now once you've done that, it's time to do some simplification. For example, when you look on the left side of our equation, the x times x minus 4 times x plus 1 on top will cancel with the same thing that's on the bottom. And that leaves us with 20x squared minus 60x plus 100. And then as for the right side of the equal sign, you'll notice with our first fraction that we have an x on top, which cancels with the x on bottom. And that leaves us with a times x minus 4 times x plus 1. And then for our second fraction, you'll see that the x minus 4 on top will cancel with the x minus 4 on bottom. And that leaves us with b times x plus 1. And then with our last fraction, we could see that we have an x plus 1 on top and an x plus 1 on bottom, which will cancel each other out, leaving us with cx times x minus 4. Now from here we want to fully simplify each of the terms. So the left side will stay the same, but on the right side, when we FOIL our first term and distribute the a across, we'll get a times x squared minus 3ax minus 4a. And then when we do the same thing with our second term, take the bx and distribute it to the x plus 1, we'll get plus bx squared plus bx. And then we'll also distribute the cx in our last term, which will give us cx squared minus 4cx. Now once we've done this, we want to group all the terms on our right side of the equation according to their terms of x. For example, we'll see that we have terms with x squared, which would be right here, here, and here. Now the coefficients on each of those are a, b, and c. So when we group those together, the coefficient for x squared will be a plus b plus c. And now we'll do the same thing with our x's. We have a negative 3ax, a bx, and a negative 4cx. So when we combine those coefficients together, we'll get a negative 3a plus b minus 4c, all times x. And then as for our constant terms, we only have a negative 4a. So for our constant, we'll have a negative 4a. Now on the left-hand side, we still have our 20x squared minus 60x plus 100. Now here comes the nifty part that will utilize some skills that you've learned in previous sections in this chapter. When we observe the expressions on the left side and on the right side of our equation, we have an x squared term, an x term, and a constant. Now on the left-hand side, we can see that the coefficient for the x squared term is 20. And on the right side, the coefficient for x squared is a plus b plus c. So based on that, we could say that a plus b plus c should equal 20. And then we could do the same thing with our x terms. On the left side, the coefficient for x is negative 60. And on the right side, the coefficient for x is negative 3a plus b minus 4c. So we could say that negative 3a plus b minus 4c should equal negative 60. And then from there, when we look at our constants, on the left side, our constant is 100, and on the right side, our constant is negative 4a. So here we can set up an equation that says our constant of negative 4a should equal the constant of 100. Now with this system of equations, we could solve for our variables a, b, and c. And when solving for this system, you could use whatever method you'd like, whether it be substitution, elimination, or even using matrices. Whichever way you choose, you should still get the same result. And in this case, when you solve the system, you should get a equals negative 25, b equals 9, and c equals 36. And once you have those values, you could plug them into our original setup. For example, a is negative 25, our b is 9, and c is 36, which will give us a result that looks like this. So the partial fraction decomposition of our original rational expression would look like this. Now let's take a look at another example. For this one, we'll want to do the same thing. We want to take this rational expression and use partial fraction decomposition to simplify it into multiple smaller fractions. So as we did before, we want to take our denominator and find all of its factors. Now as of right now, we already have a factor laid out for us, which is x. So now we need to see if x squared minus 6x plus 9 can be factored out any more than it already is, which in this case it can be. When we take x squared minus 6x plus 9 and factor it into two binomials, we'll get x minus 3 times x minus 3. Now you'll notice with this case that one of our factors are repeated. Now when this happens, there will be a slight difference in our setup. When we write out our partial fractions, we'll need to use repeated factors the same number of times as they're repeated. So when we set this up, our first fraction will have a denominator of x for our first factor, and then for our second fraction, we'll have a denominator of x minus 3, representing the first instance of that factor. And then when we show the second instance of the same factor, we'll need to have it as x minus 3, but this time it'll be squared, representing that it's the second instance. Now like we did before, we need to determine the setup for our numerators. For our first fraction, we have a first degree polynomial in the bottom, which means we need to have a constant in our numerator. Same thing when we look at our second fraction. The factor is a first degree polynomial, so we'll need to have a constant in our numerator. Now when we take a look at our last fraction, when you FOIL it out, it would technically be a second degree polynomial, but when you're setting it up, you only take the degree of the factor into consideration. So since the factor is x minus 3, which is a first degree polynomial, we still only need to have a constant in our numerator. So now we have our basic setup ready. And from here, we'll just go through the same procedure that we did with our previous example. So we want to first clear out the denominators by multiplying the entire equation by the denominator of our original rational expression. So we'd multiply everything times x minus 3 times x minus 3. So when we look at the left side, the x times x minus 3 times x minus 3 on top will cancel the same expression that is on the bottom, leaving us with a negative 27x plus 45. And then when we take a look at the right side of the equation, the x on top in our first fraction will cancel out with the x on bottom, leaving us with a times x minus 3 times x minus 3. And then for the second fraction, one of the x minus 3's on top will cancel with the x minus 3 on bottom, leaving us with b times x minus 3. Then as for our last fraction, the x minus 3 times x minus 3 on top will cancel out the x minus 3 quantity squared on bottom, because they're the same thing. And that'll leave us with a c times x. Now we want to simplify the expressions. So on the left side, we'll keep it how it is. And then on the right side, when we FOIL out the x minus 3 times x minus 3, and then distribute the a, we'll get a x squared minus 6ax plus 9a. Now when we distribute the bx to the x minus 3, we'll get bx squared minus 3bx. And then we're just left with a positive cx. Now at this point, if you remember from the previous example, we want to group all our terms together according to their coefficients of x. So for example, our coefficients for x squared will have a and b. So we'll combine those to be a plus b times x squared. And then as for our terms with x, we have a negative 6ax, a negative 3bx, and a positive cx. So when we combine those coefficients together, we'll have negative 6a minus 3b plus c. And that'll all be multiplied by x. And then as for our constant term, we only have a positive 9a. So from here, we'll just add 9a. Now we can analyze our result to create a system of equations. So when we take a look at the left-hand side, we don't have a term with x squared, which would imply that its coefficient is 0. So our coefficient of x squared on the right side, a plus b, should equal 0. And then on the left-hand side, we could also see that the coefficient for x is negative 27. So our coefficient for x on the right side of the equation, negative 6a minus 3b plus c, should equal negative 27. And then on the left side, we can see that our constant is 45, which means that our constant of 9a on the right side should also equal 45. Now that we have our system of equations, we could solve it to get the values for our variables. Now if you do this correctly, you'll get a result that says a is 5, b is negative 5, and c is negative 12. And then like before, we could plug those values in to their respective fractions. So a equals 5, and b equals negative 5, and c equals negative 12. So this would be the partial fraction decomposition of the rational expression we were given. Now that we pretty much know how to do the work involved in finding partial fraction decompositions, let's take a look at a couple more examples of how to set some up. So let's take a look at example 3. So with this expression, we have x squared plus x minus 6 all over x cubed plus 3x squared minus 2x. Now before we get set up for a partial fraction decomposition, we need to first find the factors for our denominator. So instantly we could see that each term can have an x pulled out of it. And when we do that, we'll be left with x squared plus 3x minus 2. And after a few trials and errors of trying to factor out this quadratic expression, you'll see that it cannot be factored. So it is reduced as far as it can go, which means that the two factors we'll use are x and x squared plus 3x minus 2. So let's write those denominators out. For our first one, we'll have x as our denominator, and then for our second fraction, we'll have x squared plus 3x minus 2 as our denominator. Now with our first fraction, since it's a first-degree polynomial in the denominator, we'll have a constant in the numerator. But when we take a look at our second fraction, our denominator is a second-degree polynomial, which means at the most, our numerator could be a first-degree polynomial. Now in order to express this possibility, we need to have a term with x and also a constant term. So our term with x will have some coefficient that we don't know yet, which we could represent with the letter b, and then it could also have a constant term, which we could represent with a letter we haven't used yet, such as c. Now at this point, we're all set up to find the values for a, b, and c, which you could use the same procedures from the first two examples to find those values. And if you do your algebra correctly, you'll end up with x squared plus x minus 6 equals a plus b times x squared plus 3a plus c times x plus a negative 2a. Which means that the system you'd use to solve for your variables is a plus b equals 1, and 3a plus c equals 1, and negative 2a equals negative 6. Which means the values for your variables are a equals 3, b equals negative 2, and c equals negative 8. And this gives us a result of 3 over x plus a negative 2x minus 8 all over x squared plus 3x minus 2. So that would be the partial fraction decomposition for our rational expression in this example. Now let's take a look at one more example and how to set it up. So for this one, we have 12x squared minus 4 all over x to the 5th minus 4x cubed plus 4x. Now just like before, we need to find the factors in the denominator. So the first thing we could do is pull an x out of each of the terms, which leaves us with x to the 4th minus 4x squared plus 4. Now when we take a closer look to the expression inside the parentheses, we could see that that could be factored into two binomials, which is x squared minus 2 times x squared minus 2. And in this case, you'll notice that we have two different factors, but one of them is being repeated. So similar to example 2, we'll need to use all the factors that we have in our setup, including the repeated ones. So for our first fraction, we'll have a denominator of x, and then for our second fraction, we'll have a denominator of x squared minus 2, and then for our last fraction, we'll also have a denominator of x squared minus 2, but since it's the second instance, we're going to square it. Now that we know our denominators, we need to set up what our numerators will look like. So with our first fraction, we have a first degree polynomial in our denominator, which means we'll have a constant value on top, which we could represent with the letter a. And then with our second fraction, we have a second degree polynomial on the bottom, which means that we could possibly have a first degree polynomial on top, which we could represent with the term of x with a coefficient of b plus some constant value, which we could represent with the letter c. And then as for our last fraction, we'll disregard the fact that the entire quantity is being squared and just look at the factor itself. And since the factor is x squared minus 2, it is also a second degree polynomial, which means that we could possibly have a first degree polynomial on top, which means that there could be a term with x in it with some coefficient, and there could also be a constant term in there as well. Now we've completed the setup for this partial fraction decomposition. And just like with the previous examples, you could use the same procedures to solve for your coefficients and constants. And if you did your algebra correctly, you'll end up with 12x squared minus 4 equals a plus b times x to the fourth plus c times x cubed plus a negative 4a minus 2b plus d times x squared plus a negative 2c plus e times x plus 4a, which means that the system of equations that you'll use is a plus b equals 0 and c equals 0 and negative 4a minus 2b plus d equals 12 and negative 2c plus e equals 0 and 4a equals negative 4. And the resulting values would be a equals negative 1, b equals 1, c equals 0, d equals 10, and e equals 0. So when we plug in those values, we get a is negative 1, and b is a positive 1, and c is 0, so we don't need to have it there. And then d is 10, and e is 0. So these fractions would make up the partial fraction decomposition for this example. And that wraps up the tutorial on partial fraction decomposition.